What's up, AP Physics C Mechanics students? Welcome back to our elegant physics videos. Today's topic, 5.32, so let's jump right in. Part 1, rotational mechanics, and this unit 5, we are interested in rotational motion. Everything that have been studied that is related to dynamics was more or less restricted to translational motion. We have discussed several stuff related to rotational motion like kinematics, but this was just the beginning. To complete this picture across dynamics, basically units 2, 3, and 4. So in unit 2, we have studied the forces and the laws that governs the evolution of the system, such as the Newtonian mechanics. In chapter 3 or unit 3, we have introduced a new approach to study the evolution of the system, the energetic approach. And in unit 4, we have explored the conservation of linear momentum. We're going to repeat the same concept, but after we promote them in order to make them suitable for the rotational motion. A few notions should be introduced, and to do so, we need to identify an analogy for the force or for a force in rotational motion. In the following section, we will try to introduce quantity analogy with the force, but related to rotational motion. Consider a door that can be rotated around a fixed axis along its left side. Now, from the top view, the door looks like a bar that can rotate about a fixed point. And this is how we see the door from the top view. I mean by the top view from this perspective, from above. The rotating point is known as pivot point, fulcrum, or hinge. So actually, this point is the pivot point or the fulcrum. To rotate the door, a force should be applied, and let's assume that we are applying our force exactly at this point. Then, upon rotation, this force will produce a torque. Then we will introduce a new quantity given by tau equals F perpendicular multiplied by T, where tau is the torque, the Newton meter is the unit, F perpendicular is the perpendicular component of the force applied to the body, D is the distance from the pivot point to the point where the force is applied. And actually, this is the D between the pivot point and the point of application of this force. Now, let me pay your attention that also the work is written as force times distance or displacement. Although the work is resulting from the multiplication of force and distance as well as this force times distance, but the meaning of the distance here is different. Here, the distance is the displacement, so it's associated to translational motion with the direction. And the D here does not represent any translational motion. The D here represents the distance between the point of application of the force and the pivot. So W and tau are not equal. So although they have the same unit, because the work is written as Newton dot meter or joule, also here the unit is a Newton dot meter, but again, this is not sufficient to say that the work and the torque are the same. So they are represent totally different quantity. Now, what do I mean by the F perpendicular? It means that we will consider here only the perpendicular force that cause the motion. Now, to analyze the perpendicular force, remember that this force can be decomposed into two components. The first component is in this direction, and the second component will be in that direction. Actually, we are interested only on this force, this component of the force, and this force will cause the rotational motion. The perpendicular component of the force is determined by the projection of the force along the tangential direction. So FD, actually the F should be the perpendicular force. And to find the perpendicular force, we will need to apply the projection. So we're going to consider F and cosine theta together to form the perpendicular force, multiplied by the distance between the point of application and the pivot point. And we know that any force that rotates the door in the counterclockwise direction is considered to be positive, has a positive torque. If the force is rotating the door in the clockwise direction, then the torque of this force should be negative. So this direction is the counterclockwise and this direction is the clockwise direction. Now, F is the magnitude of the applied force. D is the distance from the pivot point to the point where the force is applied, and theta is the angle between the force and the tangential direction of the rotation. Now, what do I mean by the tangential direction of the rotation? Now, let's consider here this point. During the rotation, this point will have a circular trajectory, where the pivot point will represent the center of this trajectory. Now, we can define here two axes or two directions. The first direction will be the radial direction, which is a line that is passing through the pivot. And the second direction is the tangential direction, such that this direction or this axis will be tangent to that circular path formed by this point. Now, since the F can be decomposed into two components, and by considering the angle between the tangential direction and the force, this is the tangent direction and this is the force, so we need to consider this angle. This angle is with respect to the vertical, so the force that will be projected along the vertical, this force should be written as, so the perpendicular force to the rod is the tangential force, and the tangential force is F cosine theta. Now, what about this second force? This second force is parallel to the radial direction. And for any force that is parallel to the radial direction, so let's assume that we apply the force here, which is exactly parallel to the radial direction or passes through the radial direction, then this force won't help to rotate the object clockwise or counterclockwise direction. Now, let's consider two important cases. The first case, what will happen if we apply the force in this direction? So we have a new force, let's call it F1. This force is applied toward the radial direction, and another force here, let's call it F2, that is applied perpendicular to the rod. Now, since according to the formula, we need also to consider the angle between the force and the tangential direction, we know that if the angle is zero, then cosine of zero is 1. And for F2, the angle here is zero because the angle between the force and the tangential direction is zero since F2 is parallel or toward the tangential direction. Now tau of this force, let's call it tau 2, equals. First, we need to decide the sign. Is it positive or negative? Now this force is rotating the door in this direction. If you apply this force, the door will rotate in this direction. This direction is the clockwise, and for the clockwise direction, we use minus sign. Now we write the magnitude of the force, multiply the distance, which is d, between this force and the radial direction. And since the angle is zero, and we know that the cosine is zero is 1, the tau 2 should be written in this way. Now what about F1? Now for F1, this force is passing through the radial direction, which means the angle becomes 90. We know that when the angle is 90, because this is the radial direction and this is the tangential direction for with respect to this force. If the angle is 90, then cosine of 90 is 0. And tau 2, which is equal to 0. Why it's 0? Because the cosine is 0 and 0 times E times F is 0. So for any force that is passing through the radial direction, the torque of this force will be 0. Any force is parallel to the tangential direction, the tau of this force is going to be plus minus the force times the distance. So no need to involve the cosine because the cosine in this case will be 1. For any angled force, we need to apply the original formula Fd cosine theta, where theta is the angle between the force and the tangential direction. The torque is a vector quantity, then it's associated with direction and magnitude. Now for the magnitude, we have defined how we can find the magnitude. So three factors will affect the magnitude: the force, the distance from the fulcrum or the pivot point, and the angle between the force and the tangential direction. Now, what about the direction? How we can define the direction of the torque? And apply torque that cause a body to rotate in clockwise direction. So if this force is causing the body to move in the clockwise direction, then the torque is positive and the tau is a plus Fd cosine theta. So for this particular case, the direction of this torque will be out of the plane of the page, which means the torque should be out of the screen. So imagine there is an arrow because the screen is two-dimensional region. I cannot represent an arrow that is coming out of this the page. So let's assume that we have this page in this way. So it's going out of the page or the counterclockwise direction. So it would be represented by a dot, and we use this symbol to say that we have torque outside of the page. So we draw it like this in the sketch. Now, what if we have force that is causing a body to rotate in clockwise direction, like the green one, the green force here? It's said to be negative torque, and the tau is equal minus FD cosine theta. Now, the associated vector would be pointing into the page. So imagine that there is a vector that is entering, crossing the page or the screen. We cannot represent an arrow, we cannot draw an arrow that is crossing the page. So instead of that, I will use this symbol, which is the cross, to state the direction. And the direction of the torque, because of this force, will be into the page. Now, let's solve this application. A bar of mass 2 kilogram of dimension 120 centimeter is hinged from left end and free to rotate. So the pivot or the hinge is here, or let's call it the pivot. Three forces are applied to the bar as shown. Calculate the torque produced by each force. Now, this way of representation of the force, it's not the free body diagram. And usually we don't represent the forces via the body diagram. Instead of that, we use something called the rigid body diagram. And this is what we're going to see later. Now, we have here actually three forces, external forces acting on the object. But in addition to these three forces, remember, since we have mass for the bar, then there is force of gravity acting exactly at the center of mass of the body. So this is the force of gravity here. Since the mass of the object is 2 kilogram, then the force of gravity, let's calculate the force of gravity here immediately. 2 times 10, which is 20 Newton. Now, another important force acting on the rod is exactly at the pivot, because the pivot will be fixed on a support, and due to Newton's third law for every action, there is a reaction. We'll have a reaction force from the support on the rod directed in this way. Now, for the direction, it doesn't matter to obtain the direction in a specific way, because here we are interested in finding the torque of each force. So in total here, we have five forces acting on the object, which means we need to calculate the torque of each one of them. Now let's start by finding the torque of the first force F1. Now let's draw the radial direction and the tangential direction. As you can see here, there is some angle between F1 and the tangential direction. We don't consider the 30 degree. This is not the correct angle. The angle, it should be always theta between the tangential direction. This is the tangential direction, which is perpendicular to the radial direction, and the force. And this angle is 60 degrees, since between the tangential direction and the radial direction is 90. 90 minus 30 is 60. Now we apply the torque. Torque is equal plus minus Fd cosine theta. Now, do I need to use the plus sign or the minus sign? This depends on the direction of rotation of the rod due to this force. Now, this force is rotating the rod in this way, and this is the counterclockwise direction, which means this force has a positive torque. So plus F1d cosine 60. Now the distance between this force and the pivot, we know that the total distance from the fulcrum to the end of the rod is 120 centimeter. Now, if we have 40 centimeter on the right hand side, then on the left hand side, the total distance from here to there, it will be the remaining length. So 120 minus 40, and the answer is 80 centimeter. Now, after we convert 80 centimeter into meter, and this is can be done by dividing over 100, so the distance will be 0.8. Now, F1 is 120 multiplied by the distance, which is 0.8 meter, multiplied by the cosine 60, which is 0.5, and the answer would be 48 Newton meter. Now, for tau 2, as we can see here, that tau 2 is actually passing through the radial direction. And we know that if the force is applied such that it's parallel to the radial direction or passing through the pivot point, then the tau of this force is zero, because the line of action of F2 passes through the pivot point. Now for the third force, let's draw first the tangential direction, which is perpendicular to the radial direction. Remember that the radial direction is passing through the pivot point. Now this force um, it's rotating the rod in the clockwise direction, which means the tau should be written as a negative sign. Now the force is 150. The distance between the point of application of this force and the pivot point is 35 centimeter. Remember to convert it into meter by dividing over 100. And finally, what about the angle? Now the angle here, it should be the angle between the force and the tangential direction. There is no any angle. So the angle is 0, which means the cosine will be 1. So no need to invoke the cosine in our work. And the torque 3 will be only minus, because it's rotating in the clockwise direction, F3 times D. So minus F3 is given by 150. The distance is 0.35. And the answer is minus 52.5 Newton meter. Now the fourth force is the force of the gravity here, because we are dealing here with non-negligible mass of the bar. Now we know that the force of the gravity is located at the middle, in the middle point of the rod, which means the distance from here to there is 60 centimeter, because the total length is 120 and the midpoint will be located at 60 centimeter away from the edge on both sides. Now the force of the gravity of the rod is given by mass times the gravity. The mass is 2, the gravity is 10, so this is 20 Newton. Now, three factors will affect the torque: the direction of rotation, the magnitude of the force, the distance from the radial direction, and the cosine of the angle. Let's evaluate the direction first. So this force is rotating the rod in this way. This way is a clockwise direction, which means we're going to use the minus sign. Now, what about the magnitude of the force? Is it 20? The distance is given by 0.6, because we need to divide over 100. Now, the angle here is between the tangential direction and the force. And as we can see here, the force is parallel to the tangential direction. So the angle is 0, and we know that cosine of 0 is 1. So this is the torque of the gravity. So let's complete now. Torque of gravity is minus FGD minus mg times d, and 2 times 10, which is a 20. I recalculated the force of gravity here, and the final answer will be minus 12 Newton meter. Now, what about the reaction force? The torque of the reaction force here is 0, because this force is passing through the pivot point. Any force that passing through the pivot point or parallel to the radial direction, then the torque of this force must be 0. So the torque of the reaction will be 0. Now calculate the net torque and set the direction of the rotation of the bar. Now to calculate the net torque, we need to sum up all the individual torques. So we just write tau net equals tau 1, tau 2, tau 3, tau g, and tau r. So the final answer will be minus 16.5 Newton dot meter. Now pay attention here, because the minus sign will indicate the direction of rotation. And we know that the direction of rotation is negative if the rotation is in the clockwise direction. So since the net torque is negative, then the bar will rotate clockwise in the negative direction. A meter stick of negligible mass. So since it has negligible mass, so we're gonna ignore the force of the gravity acting on this meter stick, is placed on a fulcrum at 0.4 meter mark. So the meter stick, we know that the meter stick has a length of 1 meter. So the fulcrum is located exactly at the 0.4 mark, which means the distance from here to there, it's gonna be the remaining distance is 0.6 meter. Now 0.4 plus 0.6 is 1 meter. 1 kilogram mass hung at the 0 mark. So we have hung here the 1 kilogram, if this is the 0 mark, and this is the 1 meter mark. So here we have 1 kilogram. Let's calculate the force acting on this point due to this mass. The force here is the force of gravity. This force will pull the meter stick downward, and the magnitude of this force is 1 times 10. If we consider the gravity to be 10, mass times gravity, and the answer is 10 Newton. So let me write here that this force has a magnitude of 10 Newton. Now, another mass, 0.5 kilogram, is placed on the 1 meter mark. So this is the 1 meter mark. We have placed another mass, lighter mass, 0.5 kilogram. Also, this mass will be subjected to force of gravity. So this force will rotate the meter stick in this direction due to this force of gravity. And the magnitude of this force will be 0.5 times 10, and it's going to be 5 Newton. The meter stick is held horizontal and released. Immediately after release, the magnitude of the net torque on the meter stick above the fulcrum is mass nearly. Now here we need to pay attention because we need to include all the external forces acting on the object in order to find the network. However, here I'm not going to involve the force of gravity due to the meter stick or on the meter stick because it has negligible mass. We will consider only the reaction force on the pivot. Now, let's draw the tangential direction and the radial direction quickly. This is the radial direction. And on this force, we have tangential direction here. And for this force, we have tangential directions there. Now, this force is helping the rotation, or it rotates the meter stick in this direction. And we know this direction is opposite to the clockwise direction, which means this is the counterclockwise direction. And the torque due to this force, let's call it tau 1, it's a plus force times distance. What about the angle? The angle here should be considered between the force and the tangential direction, and there is no angle here. So the angle is 0, which means cosine of 0 is equal to 1. So no need to involve the cosine here. Plus 10, the distance is defined to be the distance between the point of application of this force and the fulcrum, and this distance is 0.4. So the torque is plus 4 Newton dot meter. Now let's jump into the second force here. The second force is rotating the meter stick in the clockwise direction, so the tau must be negative. And the force here is 5. The distance is between the point of application and the force and the fulcrum. This distance is 0.6. What about the cosine? Again, this force is parallel to the tangential direction, so the cosine will be 1 because the angle is 0. And we can write now 0.6, and the answer is minus 3. Now, since this force is passing through the fulcrum, then the tau of the reaction will be 0. Now we need to find the net torque. So the net torque is equal tau 1 plus tau 2 plus the tau r. Tau r is 0. Tau 1 is given by 4. Tau 2 is given by minus 3. And the final answer is 1 Newton dot meter. So the torque will be 1 Newton dot meter, and the meter stick will rotate in the counterclockwise direction because the sign of this net torque is positive. In order to model the motion of an extinct ape, scientists measure its hand and arm bones. From shoulders to wrist, the arm bones are 0.6 meter long and their mass is 4 kilograms. From wrist to the tip of the fingers, so from wrist to the tip of the finger, this is the hand bones are 0.1 meter and their mass is 1 kilogram. In the model above, each bone is assumed to have uniform density. Now the arm is held in the horizontal. This is the arm is on the horizontal, and the hand is bent to the wrist. So the fingers point up, as we can see here in the picture. The torque exerted by the weight of the hand, which means we're going to consider here only the weight of this hand, and the weight of this hand is the force of the gravity acting downward. With respect to the shoulder is mass nearly. Now we consider the pivot to be located here. Now, so the torque is equal due to this force of gravity is given by, first of all, this force is rotating the hand in this direction. So this torque, it should be negative because this direction is the clockwise direction. The force of gravity due to this part of the hand is given by mass times gravity. The mass here is given by 1. The gravity is given by 10. So the force is 10 Newton. Now the distance is 0.6, and this force is completely parallel to the tangential direction if we assume this is the radial direction, because always the radial direction will be perpendicular to the tangential direction, and the radial direction must pass through the pivot point. So the final answer will be minus 6 Newton dot meter. Now the minus will indicate only the direction of rotation, and the correct answer as a result will be 6 Newton dot meter. The student will hold the left end of five identical meter sticks. Each meter sticks. So pay attention here. Since the student will hold the left end, it means the pivot point, it will be on the left-hand side in all of these cases. Each meter stick has a weight or weights attached to it, as shown in the figure below. In which case will the torque above the student's hand be greatest? So here, I'm not gonna find the torque due to each one of these cases. In order to save time, we're gonna use the elimination method. So remember that the torque is equal FD cosine theta. Now I'm gonna suspend the cosine theta because in all of these cases, the angle is equal to zero because the force of gravity in all of these cases will be parallel to the tangential direction. This is the radial direction through the pivot, and this is the tangential direction. So the cosine of 0 equals to 1, so this becomes 1. So only two factors will affect the result, the force and the distance. Remember that as the force increases, the tau increases. As the distance increases, the tau increases. Now here in A and B, we have the same masses, but here the distance is larger, so we're gonna eliminate A. Now let's compare between B and C. Now in B, we have 250 gram on the edge of the stick. Also here we have the same amount of mass at the same distance, but the net torque here will be larger because we have another mass placed on the meter stick. So we will eliminate B also because the torque of B is less than the torque at C. Now, what about D and E? E has a greater torque than D, and this is because the mass in E is bigger than the mass in D, and also the distance where we place the 500 gram on the meter stick is bigger than the distance here, which means definitely 300 gram case should be eliminated. Now, how we can compare between C and E? Which one will have the greatest net torque? Now, we need to calculate the torque due to each one of them. However, here we don't know what is the distance. So since we are dealing here with the meter stick, we can assume that this is 1, 2, 3, 4, 5, 6, 7, 8, 9, and here is 10. Also here we can use 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. You can use different values, but make sure that the 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 separation is the same. So you are increasing the order in a constant way or in linear way. So let's find the torque due to 250 gram. Now the force due to the 250 gram, it will be 0.25 multiplied by 10 to find the force of gravity here. And it will be 2.5 Newton. Also, this one will be the force 2.5 Newton. Now the net torque will be tau 1 plus tau 2. Tau 1 is due to the first force, 2.5 multiplied by the distance from the fulcrum. The fulcrum is here, so the distance will be 5. I'm going to assume that I'm using here the meter. You can use the centimeter instead of meter. I will assume this is meter. Um, then for the second torque is also 2.5 multiplied by this time 10. So let's calculate this. So it will be 12.5 plus 25, and the final answer would be 37.5 Newton per meter. Now, why didn't I include the signs, the correct signs for the rotation? Because here we are interested in finding the magnitude and to compare it. We don't really care about the direction. However, you can use the direction and you will get the same results, but with opposite signs. So this force here and this force here will rotate the meter stick in the clockwise direction. So instead of having plus and plus here, you can use the minus and minus because they are acting in the same direction. This is why it won't affect the result. So the answer will be exactly the same, but with the negative sign. Now, what about the last case? The tau here in the last case, we need to consider the direction of rotation. It's negative as well, but I'm not going to do that because here I'm interested in finding the magnitude. Now, the force acting here is 0.5 times 10 because the type of this force is force of gravity. And we know how to calculate the force of gravity. It's mass times the gravity. Now, mass is 0.5 times 10, and the answer is 5 Newton. So the force is 5. And the distance, I'm assuming here I'm using meter, so 8. So the final answer is 40 Newton dot meter. And as a result, since the tau produced by this force is greater than the tau produced by these two forces, then the correct answer would be. And that's it for today's lesson on 5.3 torque. Thank you for joining me. See you next time.